think we'll start, as I was just saying. So hello, Vamos viewers. So today we're fortunate to have Giulia Semeghini from the Rydberg Atom Array Group at Harvard. Giulia did her undergraduate and master's studies at the University of Milan before going on to pursue her doctorate at Lens in lattice physics of ultra-cold atoms. As a postdoc in Florence, she performed beautiful studies of quantum droplet physics in bosonic quantum gases. Since spring of 2019, she's been a postdoc on the Rydberg Tweezer project at Harvard, where she has been leading projects on studies of spin liquids and frustrated spin models. For our new viewers, you can ask questions in the YouTube chat or Zoom Q&A, which we will then communicate to Giulia at various points during her talk. And then I think with that, we can get started. So Giulia, take it away.
Okay. Hello, everyone, and thank you very much, Adam, for the very kind introduction. And thank you also for inviting me to be part of this amazing series of seminars. So today I'm very excited to share with you the results from one of the most recent projects that we did in our lab at Harvard, where we studied the emergence of these interesting topological phases in our Rydberg atom arrays. Now, first of all, let me introduce what is the general context of the work we do. We can say that the most general question that we want to answer together with a large group of researchers around the world is, how can we take advantage of all the powerful properties of quantum physics in order to, on one side, learn new things about natural phenomena, and on the other side, develop new technology? And there are several lines of research in this sense, among which the ones that we are most interested about are quantum simulation and quantum computation. So on one side, we want to use the quantum system that we have in the lab in order to study interesting quantum phenomena that could also be relevant in other physical systems. And on the other side, we want to use the same experimental setup to develop and perform some interesting quantum computation. So the two key challenges in this context are, on one side, building a large-scale quantum machine, in which the two main goals that one needs to achieve are controllability, so being able to control with high fidelity the individual qubits and their interactions, and on the other side, being able to scale these quantum systems to a large number of qubits. It's not good enough to be able to control very well a few qubits, but to have a useful quantum machine, you need a large enough system. In parallel with this, the other challenge is to develop new algorithms and new science applications that can actually be implemented on these quantum machines. Now, there are several platforms that are being used in this context, among which ions, atoms, superconducting qubits, photons, etc. And all of these have produced beautiful results over the past few years. The approach that we chose to build our own quantum machine is to use individual neutral atoms. And why did we choose those? They have a lot of properties that have proven to be very useful in this context for building a good quantum machine. For example, they can be well isolated from the environment, which is crucial for these quantum systems. They are a very well-developed toolbox in the sense that we know how to initialize, manipulate, and read out the qubit states. We know how to achieve strong interactions between the atoms, and we also know how to produce large defect-free arrays of atoms with about a few hundreds of atoms. Finally, there are many parameters in the system that can be tuned, which make this Rydberg atom array a very flexible platform. So today in particular, I'm going to talk to you about topological quantum phases. And what do they have to do with everything I was talking about right now? So these phases of matter have very unique properties. And the thing that is fascinating about them is related to this word topological. A topological property of an object is something that doesn't change when you do a continuous transformation of your object. So for example, in a topological sense, a mug is the same thing as a donut, because you see you can go from one to the other by doing a continuous transformation of the object. So to break a topological property, to change it, you really need to somehow break the system. For example, you need to cut it and glue it back in a different shape. And for this reason, due to these topological properties, these types of phases could be potentially used to implement robust quantum computation, where the idea is if we are able to encode information in these topological properties, the qubit would be very stable against external perturbations. And so this is the idea of topological quantum computation. So from this slide, you see that this work that I'm going to present to you has implications both in a quantum simulation sense, because we are studying these exotic phases of matter, but also it could be opening new directions in a quantum computation sense. So the topological phase in particular that we're interested in is the so-called quantum spin liquid. And this has been proposed about 50 years ago by Philip Anderson, with the first paper in the 70s and with the second one that is pretty famous, where he first introduced this idea of a quantum spin liquid. And the system he was studying here was a system of spin one-half particles with antiferromagnetic interactions on a frustrated lattice, as for example, a triangular lattice that I'm showing here. So his idea was that on this triangular lattice, due to the geometrical frustration, the spins would form these entangled pairs or dimers that look like this. So the state of the pair would be the superposition of up, down, and down, up. So what he proposed was that the entire system would form these pairs of spins. And as you can see, there are many possible choices that one can make for the pairing of the spins. So the ground state of the system would be a macroscopic coherent superposition of all the possible dimer configurations. And this is what he called a resonating valence bond state, where the word resonating refers to the fact that these dimers don't have a fixed configuration, but they are basically fluctuating between different orientations. Now, since this first proposal, this state has been intensively studied for the past 50 years, and a number of very interesting and exotic properties have come up. So as you see, this state doesn't have a spatial order, but it has this, let's say, hidden topological order that I mentioned before, and that I'm going to talk about later. It has long-range quantum entanglement, and the excitations that exist in this phase are these exotic anionic excitations with non-trivial statistics that we're going to mention later. And finally, among the many, let me mention what I already introduced before. There is this very interesting potential application to implement quantum computation, robust quantum computation. And a famous example in this sense is the toric code model that was introduced by Kitaev. So from all of these, you see there are many reasons why one would like to study these quantum spin liquids. But despite the huge efforts in these past 50 years, there is still no conclusive experimental evidence of the existence of this phase in any physical system. There have been some indication of a possible existence of quantum spin liquid in some condensed matter system, but still no direct evidence. So you can understand our excitement when last year, 2 theoretical groups at Harvard started looking into the possibility of creating these quantum spin liquid states using Rydberg atoms on frustrated lattices. And in these 2 works that I reported here, the groups of Subir Sachdev and Ashwin Wijnavath studied what is the phase diagram of our Rydberg atoms on 2 different types of frustrated lattices. And what they found is that indeed there are many interesting both solid and liquid phases that arise in these frustrated geometries. So of course we started looking into this in the experiment, and today I'm gonna show you the results that we got in particular for this second model. Now in this talk I will first introduce you what is the experimental setup that we're using, which are these programmable arrays of Rydberg atoms. And then I'm going to show you how we can use this system to create these quantum spin liquid phases. Finally, at the very end, I will quickly show you what are the first steps that we did in order to use this quantum spin liquid state to actually prepare a topological state. Okay, so first of all, let's see how the experiment looks like. Everything starts from a single laser beam that we shine onto a spatial light modulator. that we use to imprint a certain phase profile onto the laser beam so that we can create an arbitrary intensity pattern in the focus of a first lens. So for example, we can use this to produce this two-dimensional grid of tightly focused laser beams that are optical tweezers. So now we focus this light at the center of a vacuum chamber where we have a magneto-optical trap of rubidium-87 atoms. And so when we shine this light onto the moth, we start loading atoms into this array of traps. So what you're seeing here are many experimental repetitions in each of which we have this random loading of atoms in these traps. One thing is that you need to notice here is that in every trap, you have either one atom or zero. So these are individually trapped atoms. We have on average a 50–60% filling fraction, but as you see, this is a random distribution. So one first question is, how can we rearrange the atoms to have a desired geometry? So for example, can we fill this set of traps? And to do that, we need a second set of tweezers that we generate this time using two acousto-optical deflectors, which are useful because they allow us to move the tweezers along two directions. So what we do is that we first load the atoms in this first set of traps. So we have this initial random loading, and then we would like to move them on this top part of the array. So we turn on the traps that are generated by these acousto-optical deflectors, and then we move them during doing some procedure in order to drag the atoms from their initial positions to a final target site. So let's see how this looks in the experiment. We start with our initial random loading. And then after this sorting procedure, you see that we fill these top 300 sites with a very good probability. So we only have a few defects here and there. On average, we have about 99% filling of these traps. And so every once in a while, we also get a perfect atom array of 300 atoms. So this procedure is very flexible, so we can use it to arrange the atoms into different geometries. And to prove this flexibility even more, I want to show you that we can also, for example, draw atomic emojis, or even better, we can create small videos with an atomic Mario running around. So from these first few slides, I hope I convinced you that our experimental system allows us to create these programmable two-dimensional arrays of neutral atoms. And this is the first key element of our experiment. But then in order to do some interesting quantum physics, we would like the atoms to interact with each other. And so how do we implement that? We start with the atoms in electronic ground state G, and then we use an optical transition to excite the atoms into a Rydberg state, which is simply a highly excited electronic state. And the size of the atom when it is in this state is basically 1,000 times larger than the initial site. So when the atoms are in this Rydberg state, they interact strongly with each other via van der Waals interactions. Now, if you take two atoms at a certain distance r, and you have this coupling omega between the ground and the Rydberg state, you see that you can excite either one atom into the Rydberg state or both of them. But if you take the atoms closer to each other, this van der Waals interaction shifts the energy of the doubly excited state so much that basically the excitation of both atoms into the Rydberg state is not allowed anymore. And this is the so-called Rydberg blockade mechanism that basically tells you that when the atoms are within a certain distance from each other, you cannot excite them simultaneously to the Rydberg state. And this characteristic distance is given by the blockade radius, which is defined by this condition. So the van der Waals interactions being of the same order of the Rabi frequency omega of the transition. Okay, so with this, we added the second key element of the experiment. So we have these programmable arrays, and then we can turn on interactions by doing these transitions into the Rydberg state. Now, let's see how we can use this system, and in particular, how we can use this Rydberg blockade mechanism that I just introduced to actually create some interesting quantum many-body states. For example, as a first example, let's take the atoms on a square lattice, so on a simple geometry. And then when we turn on the light that couples the ground with the Rydberg state, the effective Hamiltonian of the system is the following. So we have a driving term that is proportional to the radio frequency of the transition omega, with sigma x being the operator that couples G with R. We have a detuning term where delta is the tuning from the Rydberg state, and Ni is the occupation of the Rydberg state at a site I of the array. And finally, we have these van der Waals interactions. So if we have a blockade radius that looks like this, so for an atom in the Rydberg state here, its 4 nearest neighbors are all blockaded, so they cannot be excited at the same time. What is the many-body ground state of this system if we have a detuning larger than 0? You see from the Hamiltonian that in this case, to minimize the energy, one wants to maximize the number of excitations, but we need to respect this constraint given by the blockade radius. So the ground state in this case is the antiferromagnetic state of the square lattice, where we have this arrangement of the Rydberg atoms into this checkerboard shape. Here, the Rydberg atoms correspond to losses during our readout procedure, and here I'm marking them with these red circles. So this is a simple example to show you how this Rydberg blockade mechanism is actually very powerful and allow us to explore interesting quantum phases. And in this paper that we recently posted on the archive, you can see how we used it to probe the entire phase diagram of the square lattice. And there is also a related work by the group of Antoine Brouets in France, who also studied this square lattice physics. Also, another recent paper that that was recently published in Science, actually yesterday. In this paper, we study instead quantum many-body dynamics in this system that are related with the presence of these quantum scars in this Rydberg Hamiltonian. Also, if you want to know a bit more about the system and our other project that we've recently done here, you can look at Hannes Pichler's VAMOS talk from a few weeks ago. Okay, so with this, I finished the introduction of the experimental setup. So if there are questions about this is a good time to take them.
Great, thank you. So we have a few questions coming in here. The first one here is from John Simon. This is a technical question about the rearrangement, which is how long does it take to do the rearrangement for the 2D arrays that you were showing? And what is the dominant source of error?
So the rearrangement takes a few tens of nanoseconds, of milliseconds, sorry. It depends a little bit on the size of the array, but typically it's about 100 milliseconds. The main source of errors are just spontaneous, like losses due to background scattering in the vacuum, and also like imperfection in this in moving these atoms around. For example, when the atoms are close to each other, the fidelity of this process is a bit smaller because you have some crosstalk between the traps when you do these movements. But yeah, I would say these are. But when the separation is good, this 99% is basically limited by vacuum lifetime.
I see. Okay. And is the fidelity with which you can actually do the rearrangement for different many-body models that you might want to look at? Does the error dictate sort of how good it has to be? In other words, are there certain ground states that you might want to look at that you can't look at because of a 99% fidelity versus a 99.9% fidelity? Or is it sort of pretty forgiving with respect to that?
So depending on what is the experiment that we're doing, we can just post-select on perfect rearrangement. So we can actually see when we had a good rearrangement and just take out those repetitions with the rearrangement. This is something that we usually do. And depending on how sensitive is the experiment to how good is the arrangement, you can set a threshold that is more or less forgiving.
Got it. And then one more follow-up question on this. Is the fidelity of the rearrangement procedure hurt at all by the particular geometry that you're using? In other words, is it easiest for the square lattice and then gets harder and harder as you get to more complicated geometries, or is in fact any geometry?
No, it is more complicated just when the atoms are closer to each other. So for example, in this experiment, they're pretty close. And so the fidelity is not as good as it is for the square lattice, but it's just a matter of distances. It's not about the geometry in itself.
Great. Okay, I think that's it for now. So let's keep going, and then I'm sure there'll be more questions later on about the physics. Thanks.
Okay. Okay, so let's now see how we can use this system to actually create these quantum spin liquids. So the geometry that we use in this case is, so we have the atoms, about 200 atoms, that we put on the links of a Kagome lattice, which also corresponds to a so-called Ruby lattice. So we start with this array and we choose the blockade radius that we can tune by tuning the distance between the atoms, but also tuning the Rabi frequency omega. We choose the blockade radius such that for an atom in the Rydberg state, all its 6 nearest neighbors are blockaded. And this gives us a constraint on the maximum density of Rydberg excitations that we can have in the system. In particular, at maximum filling, the density is 1/4. You can easily see this if you look at this cartoon. Here I have a maximum filling, and you see that for each vertex, out of the 4 atoms around it, only one of them is excited. Now, this constraint on the density allow us to map our system onto a dimer model, where basically each Rydberg excitation corresponds to a dimer on the Kagome lattice that connects the 2 adjacent vertices. So having a density of 1/4 corresponds to having each vertex of the Kagome lattice that is touched by exactly 1 dimer. So I'm going to often refer to a perfect dimer state in this talk. And what I mean with the perfect dimer state is a dimer configuration where each vertex of the lattice is touched by exactly 1 dimer. So in our system, we can also have, if we don't have maximum filling, we can also have less than 1. So 1 is the maximum. Okay, so why is this mapping into a dimer model important? As you saw before from the example of the resonating valence bond state from Anderson, these dimer models are known to have these quantum spin liquid states. So in particular, in the model that was considered in this theoretical paper that I mentioned before, they found that there is indeed a quantum spin liquid state that basically corresponds to the macroscopic coherence superposition of all the possible dimer coherence. So as you see, this is very similar to what I showed you before for this RVB state. So again, it's this coherent superposition of all the possible dimer configurations. And so this state is known to have Z2 topological order. That was indeed demonstrated in this paper. Now, what we do in the experiment is exactly the same thing that I showed you before for the square lattice. We turn on the light that couples the ground with the Rydberg state, and then we see what is the state that we get at with some state preparation. And this is an example of a single snapshot that we get at the end of our state preparation, where you see that we have indeed a dimer state, where most of the vertices are touched by exactly 1 dimer. And we have a few defects here and there where we have empty vertices. So one thing that you clearly see here is that there is no obvious spatial order. And at every repetition, we get a different disordered pattern of dimers. So of course here, sorry, I didn't say it, but the Rydberg atoms here are marked with these red dimers due to this dimer model mapping. Okay, so let's see in a bit more details how we do the state preparation and how we can characterize the state. So what we do is a quasi-adiabatic state preparation in which we slowly turn on the Rabi frequency omega, and then we do a cubic sweep of the detuning delta from negative values to positive. So at negative detuning, you have all the atoms in the ground state, and then you slowly change the detuning in order to allow for more and more Rydberg excitations. So at different endpoints of the cubic sweep, we measure the average density of Rydberg excitations. And what we see is that for delta over omega of about 3, we see that we reach this condition where we have 1/4 filling of the lattice. So this is more or less where we expect to see this quantum spin liquid state. But now how do we actually characterize it? How do we know if we have this state? So as I said before, this is expected to be a topological phase, which means that it has no local order. And so we need some non-local probe to characterize it. And in particular, we're going to use these topological string operators that were also introduced, for example, in the toric code model, which basically allow you to measure these huge many-body correlators through the system. So even if you don't know anything about the toric code, here the idea is that you want to probe the system at large distances. And so how do we define these string operators in our model? So the first one I'm going to introduce is this diagonal string operator that we call Z, which basically measures the parity of dimers along a string. So you define a Z string, which basically needs to be perpendicular to the bonds of the Kagome lattice. And you measure the parity of dimers along the string. So every time you have a dimer, you have a factor of -1. So you see that if we are in a perfect dimer phase, this is always going to be -1, because you always have exactly one dimer out of the 4 bonds that we are crossing with this small loop. If we now take a larger loop, you see that for each vertex that is enclosed by the loop, you have a -1. So that the expectation value of Z on this loop is -1 to the number of vertices enclosed by the loop, which basically means that for a perfect dimer state, you're always going to have either +1 or -1, depending on if the parity of the dimers enclosed is even or odd. Okay, so this is what happens for a perfect dimer state. And of course, if you have some defects, you're going to have a reduced amplitude. Okay, so let's see what we measure in the experiment. So here we're measuring the expectation value for Z on 2 different loops. And what we see is that for negative detuning, we start with a positive expectation value, which is a trivial result of the fact that here you have a very low number of excitations. And so most of the time, these loops basically don't cross any dimer. So most of the time you have +1. But now when you get to positive detunings here, you see that the average goes to 0. Because sometimes you get +1, sometimes you get -1, but the number of dimers you cross is not well defined. And here, when you enter this regime where the density is close to 1/4, we see that the Z parity grows to a finite expectation value. And also very interestingly, you see that the sign of this parity changes for the 2 loops. And this is because here we have 6 vertices inside, and here we have 11. And so according to this rule here, the sign needs to change according to that. Now we can zoom in into this region here and measure the Z parity for different loop sizes. And what you see here is that for all of these, we have a finite expectation value with the sign that matches the parity of vertices enclosed by the loop. Also, we see that the parity doesn't go up to 1 or -1. It's somehow reduced. And this tells us that we are indeed seeing the transition into a dimer phase, but it's a dimer phase with some density of defects that we're going to talk about in details later. But for now, we can see that we indeed see the transition into a dimer phase. So this is the first key observation here. But now, as I told you before, this quantum spin liquid state should be a coherent superposition of many different dimer coverings. So how do we probe this coherence? To do that, we need to introduce a second string operator, X, which is an off-diagonal operator. So we can define it by looking at its action on a single triangle of the Kagome lattice. So this time, the X strings are parallel to the links of the Kagome lattice. And if you apply X on this side, you're going to create or annihilate the dimer on that side, and you swap the position of the dimers on the opposite sides of the triangle. So if we use this definition, we see that if we have a closed X loop, this maps a valid dimer covering into another valid dimer covering. So we stay inside this dimer state subspace. For example, if we look at the action of these on this dimer covering, you see that we're going to annihilate these, create one here, annihilate one here, and so on. And so you get into this complementary pattern. Same thing here, you swap the position of all these dimers and you get to this. And this is true for all possible dimer coverings. So these closed X loops pair different dimer coverings. And so if we measure a finite expectation value for X on closed loops, it means that we have some coherence between different dimer coverings. Now, how do we actually measure this in the experiment? This is a very non-trivial thing that Ruben found out in his theoretical work. Basically, there is a way to do a basis rotation such that after the basis rotation, measuring Z is the same thing as measuring X on the initial state. And this basis rotation is implemented by doing a quenched time evolution of the system, where the quench Hamiltonian is simply the Rydberg Hamiltonian that I showed you before, where we quench the detuning to 0 and we change the blockade radius such that only the atoms within the same triangle are blockaded. Okay, so this is a mathematical relation. For now, just trust me that it's true. I don't have time to show you why. But so let me say it again. If we have our initial dimer state, we do this time evolution with this quench Hamiltonian and we measure Z, it's the same thing as measuring X on the initial state. So in the experiment, we do this quasi-adiabatic state preparation, and then we quench the detuning to 0, and we increase the Rabi frequency omega to change the blockade radius from 2.4 to 1.5. Here, one thing to notice is that to do this, we need to change the Rabi frequency by a factor of 14, which means that we're changing the power of one of the lasers by a factor of 200, which is something that was not obvious at all, and it took some time to actually implement. Now, the first thing we do is to calibrate. So this thing is true for a specific time tau for the time evolution. Sorry, I forgot to mention. So the first thing we need to do is to calibrate this time. So what we do is that we do this quench for a variable time, and then we measure Z on this closed loop, which is the dual loop to this closed X loop. Okay, we measure the parity and we see that we have this revival at about 30 nanoseconds, which is pretty close to the expected time from the theory. So having calibrated this time tau, we can now use this quench procedure to measure X on different loops. And what we find is that we have indeed a finite expectation value for all these loops on a large range of the tunings, which tells us that we have indeed some degree of coherence between different dimer coverings. Again, the amplitude is not 1 and it decreases with the loop size. So there is something there to be said about it. And we're gonna study this in more details later. But at this stage, we have seen that this is an approximate dimer phase and that there is coherence between the dimer coverings. So both things are consistent with our prediction for a quantum spin liquid. But now there is another thing that we need to check before putting a flag there, which is what happens if we measure open strings of these string operators. So far, I always showed you closed loops. Is there anything special about it? Yes. And actually, measuring open strings allow us to distinguish the quantum spin liquid phase from other possible nearby phases. In particular, always in the same theoretical paper, the quantum spin liquid is predicted to exist in between two other phases, where at small detuning we have a disordered phase, which is a trivial disordered phase. The density is smaller than 1/4. You have a lot of empty vertices, and it's just a disordered phase, but with nothing interesting or topological about it. And then for larger detuning, that can be a solid phase, that it's still a dimer phase, but where the dimers are arranged in an ordered state. So it turns out that we can distinguish these three phases by measuring these so-called string order parameters that were defined by these 4 people here, whose initials are BFFM. They're simply the expectation value of open Z and X strings normalized with the square root of a closed loop. Why are these interesting? These ZBFFM has an expectation value that is different from 0 only in a solid state. It basically measures correlations between the dimers. And so this is positive only if you have an ordered arrangement of the dimers. On the other hand, this X expectation value on an open string has a finite value only in this trivial disordered phase. And so the spin liquid is the only phase where both order parameters are equal to 0. And so these allow us to distinguish between these three. So we measured these in the experiment, and for X BFFM, you see that we start from a finite expectation value as expected for small detuning, and then this converges to 0 at about delta over omega of 3.5. So we see that we have a transition out of this trivial phase. On the other hand, if we measure Z BFFM, we see that this is consistent with 0 on the entire range of the tunings that we probe, which means that it doesn't seem like we have any solid phase. We don't seem to observe any solid phase here. So putting this together with the previous measurements, we can identify a region that is compatible with a quantum spin liquid. More precisely, we have said that the finite expectation value for closed loops on Z told us that we are in an approximate dimer phase. The finite expectation value for X told us that we have some coherence. And finally, with these open strings, we have excluded the possibility of having other trivial phases. So all of these allow us to say that the state we are preparing is consistent with a quantum spin liquid, according to the definition that we gave at the beginning. And here I want to stress one of the main novelty of this work is that we actually have access to these string operators, which allow us to get positive indications about the existence of this quantum spin liquid, which is something that usually is missing in most condensed matter experiments. Now, as I said before, the fact that we observe reduced amplitudes, for example, for the Z parity, means that we have an imperfect dimer phase. And in particular, this is caused by a finite density of empty vertices that we're gonna call monomers. So monomers is simply a vertex that is touched by no dimers. And why does this affect the measure Z parity? Looking at the simple example that I made before, if you have a perfect dimer state, this loop will always give expectation value of 1, because this is simply determined by the number of vertices enclosed. But now if you remove a dimer and you create a monomer here, you see that the parity flips from +1 to -1. So now if you have a finite density of monomers, when you measure the expectation value for Z, the amplitude of this expectation value will be rescaled by the number of monomers that are enclosed in the loop. And so this will generally be smaller than 1 for a finite density of monomers. So we can actually, from the single snapshots of each experimental repetition, we can measure how many monomers we have. So we measure the probability of observing dimers, so the good vertices, the ones that are touched by exactly 1 dimer, monomers, which are exactly this thing, and also we have a finite probability of having double dimers, meaning we have 2 dimers touching the vertex, which correspond to weak violations of this blockade, of this Rydberg blockade. So what we see here is that in the relevant range of the tunings, we have a density of monomers that is about 0.15 per vertex. Now, these monomers correspond to a specific type of quasi-particle excitations that is called an electronic anion in this topological language. Now, another way to detect the presence of these single snapshots is to deduce the density of these monomers by looking at the scaling of Z with the loop size. In particular, if we have uncorrelated anions, and this means that each vertex has a certain probability of being empty. And so the expectation value of Z scales, so the proportion to the area of the loop. So Z should scale with the area of the loop. If you have instead correlated anions that have short range correlation length, if both anions are inside the loop, it doesn't matter because the parity doesn't change. The contribution of the two anions cancel out. It only matters if the pair sits across the loop so that one is inside and one is outside. So expect that the parity scales with the perimeter of the loop. So we actually rescale the measured density here, either with the area or the perimeter of the loops. And what we see is that for small loops, this is approximately a good scaling with the area of the loop, which is consistent with what we measure. We have some density of monomers that are scattered around. But for larger loops, we see a deviation from this behavior, which gets closer to a perimeter law. So this is something that we're still trying to understand, but it might be that there is some degree of correlations between these excitations. Now, another type of excitations that can exist in the system is the so-called magnetic anion, which basically correspond to a phase error in the quantum spin liquid state. To see here in this cartoon is that if you have M anions, you're basically adding a -1 phase factor to some of the dimer coverings. And so, which is different from the quantum spin liquid, which has +1 factors on each dimer state. Now, analogously to what I just told you about Z loops and E anions, one can detect these magnetic anions using the scaling of closed X loops. In particular, we do this rescaling with the perimeter in this case. And we see that for M anions, we have a very good perimeter law scaling with the loop size. So this tells us that the M anions indeed seem to be correlated with each other. Now, I just wanted to flesh out this discussion, which is something that we basically understood yesterday and that we're still trying to understand. But the idea here of this whole study about the quasi-particle excitations is that the state we're preparing is clearly not the ground state because we have a finite density of excitations. It is a non-equilibrium state, but at the same time, it has all the quantum spin liquid properties that I showed you before, which is very interesting because it means that if we cannot prepare the ground state, which we typically cannot in a realistic experiment, it's not the end of the world. We still have a state which has quantum spin liquid properties in the experiment, which is great, I think. So with this, I finished the second part. So it's a good time to take a few more questions. I still have like 5 minutes, so let me know if you want to stop here or I should finish.
I think I can ask a few questions here. And just so you know, we've actually lost your video feed, Giulia, but we can hear you fine. So maybe we can keep going, but at the end, if it's an issue, we can address it.
Okay.
You should turn your lights back on, Giulia. It's really dark over there.
Sorry, usually we keep John muted. So we have a couple questions here. So the first one is from Marcus Bins, excuse me, who asks, does it worry you that there's no clear plateau of the n equals a quarter as you sweep delta over omega?
No, it doesn't. Well, I mean, in principle, it could. I think, yeah. So you have this quasi adiabatic preparation. So of course, you're not able to do the plateau is what you see in the theory, but of course we don't see it in the experiment. I think what really is important here is that these string operators give all the proper results, and so the fact that the density is not exactly 1/4 on the entire range is not too important in this case.
Okay. Another question is from Francisco Machado, who asks, you had mentioned that the scaling of the value of the loop operators with the size of the loops allows you to conclude the presence of a finite density of monomers. Does this allow you to estimate the temperature of the state that you've adiabatically prepared?
I think we might have just lost.
I think we just lost Giulia. Yeah.
Hopefully she'll rejoin.
Yeah, we can just hang out here. John, now is a moment where you can entertain us.
Yeah, exactly.
Okay. So do you think we should just try answering the
I
question?
was going to make the same comment.
Yeah. I had a related question, which is about the preparation timescale, right? Like, how long do these sweeps take? So,
you saying you want to go over under on it, or what's?
Yeah. Okay. So
Julia,
you're
hey,
back. Welcome. We have so many questions for you.
No. You should join quickly so that John doesn't continue talking. Okay, great.
Hey.
Okay, sorry about that.
No worries. And if we run over a little bit, it's not a big deal, so don't worry about it. Okay. I don't know if you heard the question, but it was you had mentioned that the scaling of the value of the loop operators with the size of the loop allows you to conclude the presence of a finite density of monomers. Does this allow you to estimate a temperature? And if it does, is it below the gap that you would expect for the QSL ground state? Which of course is a little bit, you were just talking about how this is a non-equilibrium state and that you're actually excited above it. But I think in general, it's an interesting question how the temperature that you might infer compares to a gap that you might infer.
So this is a great question, actually, and there is a lot to talk about here. But actually, what we found out recently is that basically in the theoretical model initially considered a simplified interaction potential, which is not the 1/r to the 6. It's just a PXP model with this square potential. And there you have this nice spin liquid ground state. If you start including this 1/r to the 6 with all the relevant long-range interactions, it looks like the quantum spin liquid ground state disappears. But now, if you do a dynamical preparation of the state, instead of going to the actual ground state, which is a solid phase, this VBS phase, you actually end up in something that has all these good quantum spin liquid properties. So it seems that the fact that we cannot actually be adiabatic is the fact that allows us to see this quantum spin liquid. So we haven't tried to estimate the temperature. Maybe we could. But just to flesh this out, this is actually what it, so from dynamical simulations, it seems that we're indeed not able to go close enough to the ground state, but this is actually what allows us to see the quantum spin liquid. And maybe we can discuss this more in details later.
Got it. And maybe I'll ask one more question here. This one's from Monica. So can you elaborate on the equivalence between a Rydberg excitation in your experiment and a singlet in Anderson's RBB state? As far as the topological physics is concerned, are there any important differences between these two physical manifestations of a dimer?
So I would say that what you really need to have this quantum spin liquid state is that these dimers, whatever they are, either pairs or spins or these Rydberg excitations, have this frustration on these models such that the ground state has these resonances between different dimers. So of course it's a different state, and actually this prediction from Anderson turned out to be not exactly true. So on the triangular lattice, you don't have a VBS, but what you need is just to have these resonances that allow you to have this long-range quantum entanglement. I think that is the key point of these dimer models, these resonances. I don't know if I answered the question, but
no, you didn't. Okay, great. Let's keep going. There are more questions, but we can save them for the end and as well for the post-Vamos discussion. Great.
Okay. So the final thing that I want to talk to you about is how we can use this quantum spin liquid to create some topological states. So we started looking into this, and this is where we got to. So first of all, we need a system with a non-trivial topology. And so to do that, we basically cut a hole in the middle of the array by removing 3 atoms from a central triangle. So we just remove these atoms, and so we create an inner boundary of the array. Now, when we do this, we basically separate the dimer states into 2 distinct topological sectors, which simply means that the dimer states that are in different topological sectors can only be transformed into each other if you do a highly non-local transformation, which is the same idea that I told you before about the mug. Like the mug and the donut are in the same topological sector, whereas everything that you need to create by breaking the donut is in a different topological sector. It's the same idea. And so, for example, how can we see if these dimer states that I'm showing here are in the same or in different topological sectors? So we built a transition graph, which is simply the superposition of the two dimer coherents. And then we remove all the dimers that overlap with each other. So we end up with something like this. We do the same for these two states, and then we get this. And here you see that the main difference is that here we have this closed loop of dimers that goes around the hole, which shows you what is the process that you need to make to transform one into the other. You need to do this operation that involves about 15, here it's like 20 dimers. But here the idea is, since you have to do this non-local operation that goes around the hole, these two states are in two opposite topological sectors, whereas these one are in the same. Now we can define the logical states in this system as the superpositions of all the dimer states in the two topological sector. So we call 0 the superposition of all the states in topological sector 0 and 1 the other. Now, one thing that we want to notice here is that if we measure this Z string operator on any string that goes from the hole to the boundary, this has a very well-defined expectation value within each topological sector, but opposite expectation values in the two sectors. So you see here we cross one dimer, and here we cross 0. And this is true for every dimer state in these topological sectors and for any hole to boundary string. So these allow us to identify a first logical operator, sigma z, as any of these strings from hole to boundary. So the eigenstates of this logical operator are 0, are the topological sectors 0 and 1 with eigenstates minus and plus 1. Now, the second logical operator can be defined as any closed loop that goes around the hole, closed X loop that goes around the hole. And here the eigenstates are the even and odd superposition of the two topological sectors, and they have eigenvalues plus and minus 1. So what we can do is we repeat the same quasi-derivative preparation that we did before using this geometry with the hole, and this is what we measure. So for sigma z, we see that this goes to 0 after delta over omega of 3, which means that we are in a superposition of the two topological sectors. So 50% of the time we get plus 1, 50% of the time we get minus 1. Instead, for the sigma x operator, we see that this is finite and positive up to 4.5 delta over omega, which tells us that in this region where we have identified this onset of a quantum spin liquid phase, the state we are preparing has a finite overlap with this plus state. Okay, another check that we can do is measuring correlations between these hole to boundary strings. So here we take these pairs of strings and we measure the correlations between them. And these are expected to have the same expectation value for all dimer states independent of the topological sector, because the expectation value only depends on the number of vertices between the two strings, again, because you can interpret this as a closed loop that closes outside of the array. So indeed, we see that for these correlations, we have a finite expectation value, whereas for a single string, we had 0. Okay, so all of this is just to say that these are the very first steps towards having a topological qubit, in the sense that we create this non-trivial topology. We see how we can define the logical states and the logical operators. And we indeed see that we can prepare with some small but finite overlap one of the qubit states. Now, there is a lot more work to do to actually make this topological qubit good and useful. But these are at least the very first steps in that direction. So to conclude, I just want to summarize what I showed you today, which is that we observe this transition into a dimer phase with no spatial order. We have evidence for the presence of coherences between different dimer coverings. We have the first signatures of some non-trivial topological order. But then there are a lot of open questions that still need to be investigated. So for example, I told you, we believe this is a metastable state, and answering the question before, we know that this is a quite important thing to actually be able to observe this quantum spin liquid. So there is something that needs to be fully understood. Then we would like to improve the state preparation, but also the measurement of the string operators. And finally, the most exciting thing, of course, is to understand how to encode and manipulate these topological qubits. So with this, I'm done. I just want to show you what our experiment looked like over the past year of pandemic. So 1 year ago, we were kicked out of the lab. And so we installed all these security cameras to keep an eye on the lab and actually to be able to control the experiment remotely. So this is us on about a year ago, the last day that we were in the lab after a few crazy days in which we tried to put everything online to be able to run the experiment from home. And that was actually very successful, thanks to my amazing colleagues, because all the data that I showed you today were taken from our home. So this is pretty impressive. I would have never believed that if you told me 2 years ago. And this is us last summer when we finally could meet outside in a socially distant lunch. So with this, I just want to acknowledge all the people that worked on this project. Again, this is the team of my amazing colleagues in the lab. These are the PIs that lead this project. In particular, Misha is the main PI here. And finally, you see that we have this big team of theory collaborators, because as you can imagine, this was a hard project to work on, also on a theoretical point of view. And in particular, I want to thank Ruben and Hannes, who had the patience of teaching me about toric code and lattice gauge theories and things like that. So with this, I just want to thank you all for your attention. And if there are any more questions, I'm happy to answer.
Thank you for the great talk. Okay, so we have a bunch of questions here. Let's sort of get through some number of them, and then people can talk with you afterward too. So the first question here is from Dan Stemper-Kern, who asks about your statement that you have a non-equilibrium state. Is the state you produce a mixture or a superposition of many energy eigenstates, or is it the ground state of a defective lattice system? Can you tell the difference?
So that's a good question. So yeah, I don't know if we know exactly. So we know that we have this finite density of excitations, and we are still trying to understand exactly what times and how correlated or uncorrelated they are, because that is actually important. We know that, you know, in this quasi-diabatic preparation, we have an effective finite temperature. So in that sense, it's an excited state with, you know, we have a superposition of states that are not exactly dimer states. So they have these excitations in them. So I don't know what to say more about this. Again, these are things that we're understanding in these days. So I think that's the best I can say for now.
Yeah, great. So then another question from Chris Lauman is, from my understanding, one of the really cool features of the toric code is that it has quasi-particle excitations, which are fermionic, despite the fact that the negative degrees of freedom might be bosonic. Is it possible to probe this experimentally? And, you know, could there be indirect signatures that are not as hard as braiding?
So these quasi-particles that I showed are all bosonic, and I know there are these fermionic quasi-particles that I don't think we know yet how to create experimentally. I don't think that's one thing that we know. We have some ideas of how to do some kind of braiding by using, so for example, an E anion is just a defect. You know, you have this empty vertex. So in principle, you can create it in a certain site by applying, for example, a local detuning. And then you can, in principle, move it around, moving the laser beam that controls this detuning. And so this is this sort of grading where when you move this EN around. These are some of the ideas that we started to discuss. It's not, I would say that for this fermionic excitation, there is not a clear idea yet.
Got it, okay. So then another question from Tommy Schuster is, the Z-loop operators look like they have a finite value over quite a large width in delta over omega. Does this mean that the dimer phase is stable over a large regime of parameters? And is this consistent with numerical simulations?
So it is quite a large range. It's about 1.5 delta over omega. It is consistent in a sense with the simulations. I mean, of course, the simulations cannot exactly reproduce our system. So, for example, okay, so the original simulations with this approximate model give very different results. So the range is smaller, it happens at different tunings and so on, but this is clearly understood because of the difference in the interaction potential. Now, these latest dynamical simulations match quite well. So for example, the delta, the tuning where we see the transition is very close, around 3 delta over omega. The range over which this spin liquid phase expands, I think it's close. I don't remember exactly if the two ranges matches perfectly, but you need to take into account that this is a much smaller system with periodic boundary conditions. So I would say that the comparison is not super close. So it gives some indications, but I think a one-to-one comparison is very hard.
Got it. Okay. And you know what, I think we should probably stop there. So if you wouldn't mind unsharing your screen so I can broadcast the talks for next week. Thank you. And just as I'm bringing this up, a reminder that in a moment there will be a link posted in the chat for where to go for the post-Vamos discussion with Giulia. Can everyone see this? Yeah, good. Okay, so we have upcoming talks here, both at the Quantum Science Seminar Series in Europe and also Vamos. So actually, Monica will be speaking next week at the Quantum Sciences Seminar, and then on Friday next week, we'll have Andrew J.H. So with that, hopefully see you in the post-Vamos discussion. Thank you again, Giulia.
Thank you.